Thank you very much. This is Chapter 11. We have 2 days to do Chapter 11. Maybe I'll just get done in 1 day. It's hard to say.
Just get it done.
Yeah. The world has resistors in them. You can look around the room and know who they are, right? And then the world has inductors in them. And you can look around the room and see who's just a coil of wire sitting there. And you know who they are. And now we're going to have to do something with them. We're going to have to put them in series. So does it matter if I put them in series like that, or if I put them in series like this? Would it make any difference?
Yes.
And the answer is no. It doesn't matter who comes first and who comes second. They're going to have the same current. They're going to have the same power. They're going to have the same impedance. Either way, it doesn't matter. Okay, so now if I go in and I need, when I have, if I go and I take a circuit and I take a battery and I go and I put a resistor and I put an inductor in there, what's going to happen? 10 volts, 10 ohms, 10 to the 6 Henry. What's going to happen? Well, the x of L is 2 pi f L. What's the frequency of a DC circuit? 0. So this is 0, so the current is going to be 10 volts divided by 10 ohms. I'm going to have 1 amp flowing, and no one is going to care about the number of turns in that coil. It's totally irrelevant. It's all it is a straight hunk of wire that happens to be wound up. Okay, so in general, except maybe on a test where I'm trying to hose you over, there'd be no reason to use an inductor in a DC circuit. Okay, so now I do the same thing. I have some AC circuit. I've got a resistor. I've got an inductor. There's some voltage across the resistor, and there's some voltage across the inductor. And we're just going to talk about them in general. And there's some voltage that's the source. All right, so what is that voltage source going to be? Voltage source is going to be the square root of the voltage across the inductor squared plus the voltage across the resistor squared. Now, why is that? Well, there's some impedance caused by this circuit. So this circuit has some resistance R and some X of L, which is the 2 pi FL. The resistance is at an angle of 0. The impedance is at an angle of 90 degrees. Okay, so if I look at 90 degrees, that's up this way, also known as the y-axis, also known as the imaginary axis. And the real guy is sitting on the x-axis going that way, and they're perpendicular to each other. So now I have so much up here, so much over there. I come over there. Now I got a right triangle, and I have the impedance is sitting on the hypotenuse. The hypotenuse is equal to the square root of whatever. So the impedance of the circuit is going to be R squared plus X of L squared. The total voltage is going to be the square root of X squared plus X of L squared. Now this is a source voltage, so I know what it is already, right? So that's a known. If I know this guy, I can calculate that guy. You know, 3 equations, 1 unknown. As long as I only have 1 unknown, I'm okay. So, but I'm looking at it as a Pythagorean Theorem thing. If I have a right triangle, A, B, C, then C squared is equal to A squared plus B squared, given to us by the Greeks 2,500 years ago. So the Greeks didn't know about electricity 2,500 years ago, but the Pythagorean theorem that they left us applies to a resistive inductive circuit. If I want to know this angle, theta, I would say, well, theta is equal to the arctangent of the B over A, And I'd always put it in absolute value so that I get a first quadrant answer. So I look at my XY coordinate thing again, and this is my first quadrant, that's my second quadrant, third quadrant, and a fourth quadrant. And if I look at tangent, tangent's going to be positive in the first quadrant, it's going to be positive in the third quadrant, it's going to be negative in the second and the fourth quadrant. Just one of those things. And so when I look at the angle, I always look at it as a first quadrant thing. We call that a reference angle. And then if we need to find what the real angle is, we do that from the reference angle. Do I need to go over that for a couple seconds? So if I'm in the first quadrant, my angle is my reference angle. If I'm in the second quadrant, then my angle is 180 degrees, which is a straight line type thing, minus the reference angle. And if I'm in the third quadrant, it's 180 degrees plus the reference angle. And if I'm in the fourth quadrant, my angle is going to be 360 minus the reference angle. I can do that all over again in radians. If I want to, I'm not going to do that. Okay, so I won't do it over again in radians. So when I look at, I've got some resistance, and I have some X of L, and I have some impedance Z, and I have some angle theta. Well, that angle theta becomes the arctangent absolute value, so I'm in the first quadrant, although I'm already in the first quadrant, the X of L value divided by the R value. And X of L is something I'm calculating, that's going to be 2 pi FL. So I'm going to be doing a calculation to get it. It's in ohms. It's in imaginary ohms. I can think of an I sitting there. I can think of angle 90 sitting there. Or I can ignore those thoughts at all and just remember that it's going to be on the y-axis. Okay, there's some phase shift associated with this. That phase shift is that angle theta. So that impedance is causing a phase shift. V is still equal to IR. Voltage is equal to current times impedance. That impedance has an angle associated with it. Voltage probably doesn't. If it does, the angle 0 of the source voltage. Therefore, the current will have some angle associated with it. Current is going to be voltage divided by impedance. So whatever angle is associated with impedance, let's say it's angle 30, just for the heck of it, then my current is going to be V over Z, angle minus 30. So Eli the Iceman says that voltage leads current. Well, if current is minus 30 and voltage is at 0, then it certainly is leading it. So that's how that happens. All right. Happy about that? Yeah, why not? All right. So now we're going to put these things in series, and we have some voltage, what we'll do is we'll open up multisim just in case we want to use it later, right? All right, so I've got some inductor and some resistor, and so I got 12 volts and I got 13 kilohertz. And I got a resistor, 1K, that sounds good. And I've got a inductor, 10 millihenry. Let's see, will that be enough? All right, so X of L is going to be 2 pi 13K 10 millihenry. Oh, that's not very much fun. Oh, that's good. That's a good number. Is that a good number? 2 times pi times 13 times 10. So that gives me 817 ohms. 817 ohms. So I've got an impedance that is going to be the square root of 1K squared plus 817 squared. And we'll try to control our square root sign so that it's reasonably sized. So my impedance is what? I don't know. 1,000 squared plus 817 squared equals square root 1,300. Okay, so 1.3K. 1.3K. And our angle is going to be the arctangent of the x of L, 817 divided by 1,000, which would be something less than 45 degrees. Unless, of course, I don't put enough zeros here and the front row complains about it and then I got to change it. I would have put it in my calculator right. 39. So I got a phase shift of 39 degrees in that impedance. So the magnitude of the impedance is 1.3K with an angle of 39 degrees. And then I asked myself, what is the current? Well, current has to be voltage divided by impedance. Anybody remember the voltage? 12 volts divided by 1.3K angle 39. 112 divided by 1.3K. Oh, I don't know. 930. 920 microamps angle minus 39. When I'm positive and I'm dividing, it becomes negative on top. Although it looks sort of weird, so I'll write it over here. Actually, it's 9.2 milliamps angle minus 39. For those that put it in their calculator and got the right answer, unlike me, who with his trifocal saw it differently until I looked at it again. We want to know the voltage across the resistor. What's the voltage across the resistor? Well, it'd be whatever the total voltage is times the resistance. What's the resistance? 13K divided by the resistance. Resistance is 1K. 1,000 ohms divided by 1,300 ohms angle 39. So the voltage across the resistor, 12 times 1,000 divided by 1,300, magnitude 9.2 volts. Well, I could have gone and taken the current too, I guess. Multiplied times the resistance. Angle minus 39 degrees. What is the voltage across the inductor? Voltage across the inductor. Well, we'll go V is equal to IR, right? So we'll do that. 817 angle 90 times, well, that's the, we'll write it the other way. E is equal to ZI. Yeah, is that better? So I got the Z and 9.2 milliamps angle minus 39, and I ran out of room again. And we multiply the magnitudes. 7.5 volts angle 90 minus 39, 51 degrees. Volts, angle 59 degrees. Now, you notice that the voltage across the inductor being at 51 and the voltage across the resistor being at minus 39, they are still 90 degrees out of phase, right? So that's a 90 degrees difference. So the voltage source had best be the square root of voltage across the resistor squared plus voltage across the inductor squared. That better be the same. So what's the source voltage? Anybody remember? 12 volts. So 12 volts had best be the square root of, this is 7.5 squared. Well, maybe it is. It's hard to say. Didn't look like it there. 7.5 squared. And the voltage across the inductor was 9.2. Oh, 9.2. Across the resistor. So that had better be true. And if that's not true, then we'd better go back to the drawing board and do something. Who put that equal sign there? Raimundo, did you do that? Oh, that was Enrique that did that? All right, typical. 9.2 squared plus 7.5 squared equals square root. And I see 11.8697, looks like 12 to me, so it must be true. So I'd round it off, because I'm not carrying very many significant digits with me. So all that would be true. Yeah, that's nothing overly important there. All right, let's work some problems before we go on. See if there's any good problems to work. Number 2 looks like a good one. How do I know? I'm not there. Tell me when you get there. Oh, there we go. So page 357 for those that can't find that on their own for some reason.
Thank you.
All right, so the component voltages shown in B are taken using an AC voltmeter. Determine the magnitude and angle of the source voltage. Okay, so I know I got a source voltage, and I got an inductor, and I got a resistor.
You're doing number 1, 2.
Number 2. And I have 10 volts, and I have 30 volts. Am I not doing number 2? Yeah. Are you complaining about the difference between my inductor and resistor?
No, I just didn't know what problem we started on.
Oh, I see. Oh, you're complaining about this number 2. There.
Yeah, there you go.
Yeah, is that better? All right.
That's better.
Well, I think I complain about the way I do the inductor and the resistor, because those are really bad.
It doesn't matter.
I mean, it doesn't matter. It's exactly. It really doesn't matter much. I mean, it is what it is. Okay, so voltage source has to be the square root of 10 squared plus 30 squared. So that's the square root of 1,000, which is 10, the square root of 10. And of course, we wouldn't probably wouldn't keep it that way, right? So we probably say 31.6 volts. And then we say, well, what angle is it? Well, the phase angle has to be the arctangent of something. Hard to say. Of 10. 10 over 30? Yeah, the arctangent of 10 over 30.
-1.
What? 10 divided by 30 equals arctangent. Well, that was bad. 10 divided by 30 equals arc tangent 18.4 degrees. Yeah, second function tangent key. Alright, well, that was number 2. Hope they're all that easy. Okay, we're going to do number 6 next. Well, why don't we go back and do number 2 again?
Number 2 again.
Yeah. So,
What was the 1,000?
yeah, we'll do it again. Why not? See, we need a resistor. Well, all right, so I got a resistor, and I've got an inductor, all right, and I've got a voltage source. Anybody complaining yet? Got a voltage source, and I got a ground, and I got 2 voltmeters. Oh, I don't want that voltmeter. I want this voltmeter. 1, 2. I'll get rid of this guy. Where's my delete button? Oh, yeah, there we go. Get rid of this guy too. We don't want him. All right, and we want these guys going the other way. Hit the right button. So we okay so far? Okay, move these guys. Don't want to move that. Move this guy. Yeah. Now, if I had somebody out there, I could start complaining pretty quick.
You should have 2 grounds.
Okay. These guys have to be AC, right?
Yes.
So if they're not AC, then
Gotcha.
that
Somehow
would be
Chris get it right.
Yeah.
AC.
AC. Yeah, I got to be AC. Okay, so I turn it on, and I got 0.3, and I got 120. Excellent. Now the problem requires me to have 10 and 20 in order to know my now I got to make this 10, and I have to make that 20, and this one will come out with the right answer, right? No, it can't. So I've got 1, 2, 3 unknowns. I can't possibly solve the problem this way, right? Totally impossible. What did we say the voltage was going to be?
10:30.
13.6.
Yeah.
All right. But is that 31.6 peak or RMS?
That's what he did.
That's RMS. Because these are RMS meters saying 10 and 32. So we're going to make this guy 31.6. Do we know the frequency?
Yes.
No. We don't know the frequency. Okay, so that makes us pretty hosed, right? But now we have 0.09 here, and we have 31 there. We want 10 and 30, right? 10 and 30. So this guy, we want to make him more, right? More? All right, so we'll make him more. How much more do you want?
Twice that.
Yeah, how about 20 times? Because that's what I got. All right, so now I've got 1.7 and I have 3.1. All right, so I still want to get this guy up to 10. I want this guy to be at 10, that guy to be at 30, right? So I'm going to multiply by 5 more. 5 times that, so that'd be 100. Turn it off. Okay, so I want 100 milli. Okay, now I got 6 and 30, so I just want a hair more. I don't want a whole lot more.
120?
I don't think I can just type in 120, can I? All right, we'll put in 120. Oh, too much. Too much. We can tweak on the bottom guy though, right? 115? 115, yes. No.
18.
18? 17?
17?
We'll try 117. 119? Oh, 117 wasn't enough. 117.5? 0.5. 0.6? Do 0.6? All right. Ooh, not enough.
9.
That's close, huh?
Yeah, 18's gonna be it.
0.8? 0.9? 0.8?
There you go.
0.8? Not bad. Not bad. So I have 31.6 was the answer I got. I have 10 volts and 30 volts, and it looks like it works. Okay, now I wouldn't have done that. I would have gone back and done something else. But you know, it's always good to have MoleSim help out, right? Okay, so number 6. Calculate everything that you can possibly calculate in the figure below. Okay, well that seems reasonable. Don't leave anything out. Okay, so I got 10 volts, and I got 24 kilohertz. Okay, and then I come over here and I got an inductor, and I got a resistor. We'll make the inductor look prettier. That looked better.
You like that?
So L is 2.2 millihenry. And R is 120 ohms. And Raimundo doesn't like that equal sign being that way, so I have to change it before Chris complains. Okay, so I'm looking for impedance. I'm looking for total current. I'm looking for voltage across the inductor. Looking for voltage across the resistor. And I'm looking for the phase angle. Alright, so that's all that I'm looking for. But in order to get that, I'm going to have to figure out what x sub L is. Okay, so x sub L is 2 pi 24k 2.2 milli. Okay, at that point you take out your calculator. 2 times third function pi times 24 times 2.2. The kilo and the milli cancel out, so I don't have to put them in. 332 ohms. 332 ohms. Angle 90 degrees, if anybody cares. We may or may not care, it's hard to say. Alright, so of all the things that we can calculate, which one do you want to calculate first? Okay, so the arc tangent, absolute value, not that anything's negative, of x of L, 332 divided by the resistance, 120. It's 332 divided by 120 arc tangent, 70 degrees. 70.1 degrees? We don't have that many significant digits. 70 degrees. All right. So now we're going to calculate the impedance next. Square root of 120 squared plus 332 squared equals 120 squared plus 332 squared equals square root 353 ohms at an angle of 70 degrees, which is exactly why Raimundo told us to calculate the angle first, because we're going to need it in the other things. All right, now, total current is going to be the voltage divided by the impedance. The voltage is 10 divided by 353 angle 70 degrees. 10 divided by 353. You handle the magnitude first. 28 milliamps angle minus 70. The voltage across the inductor, X sub L, times the total current. If I could spell total current, which I obviously can't. All right, so that'd be good. 332 ohms, angle 70, times 28 milliamps, angle minus 70. That's pretty weird, isn't it? Wonder how that happened. All right, so I got the milliamps times 332 ohm, 9.4 volts. The angle across the resistance times the current, was it 120 ohms times 28 milliamps, angle minus 70, 120 times 0.028, 3.4 volts, angle minus 70. All right, what did we leave out? Oh, we didn't leave anything out. We're done.
Bam.
Yeah. Oh, hit the wrong button. View, zoom, 100%. There, now you can see more. Now, I don't like that the impedance of the voltage across the inductor has 0 angle, and the voltage across the resistor has a minus 70 angle. But other than that, everything seems to be all right. All right, that was 6. Next guy is 18, and we can't do 18 yet because we haven't gone that far. So why don't we do, well, all the rest of them are the same, so it doesn't, yeah. We could do 8. Could we do 8?
Let's call
We could, yeah, want to do 8?
it.
No, we still have to cover apparent power and whatever power and things like that. We'll do number 8. All right, so I've got 5 volts and 20K. And I've got an inductor and a resistor and a resistor and an inductor. And I have an L1, 15 millihenry. And I've got an R1, 220 ohms. And I've got an R2, 330 ohms. And I've got an L2, 330 microhenry. Okay, so what do I need? I need, before I do anything, I need an X of L1. 2 pi 20k 15 milli. Okay, so 2 times pi times 20 times 15, 1.9k. Really? 1.9k? I don't think so. 2 times pi times 20 times 15. Yeah, I guess it is. 1.9k. Angle 90. 1.9k. And then we're going to do the next one. 2 times pi times 20 times 0.33. 41.
What was that for?
41. 41 ohms. Alright, so now we have everything we want. Now we're going to go and see what we need. What do we need? We need the impedance. We need the total current. We need the voltage across inductor 1. The voltage across resistor 1, the voltage across inductor 2, the voltage across resistor 2, and the phase angle. Alright, so that's what we're going to do. We'll go for impedance first. We will?
Are you gonna get the angle first?
Huh?
We're gonna get the angle first.
No, not this time. So impedance, square root of 550 squared plus probably 1.9k because I round that up.
Is that the sum of all the resistors, or?
No, one's the sum of the resistors squared, the other one's the sum of the inductors squared.
Okay.
But because that other inductor is only 41 ohms and it was 18 something, and I rounded it up to 1.9k, I just kept it that way. 1900 squared plus 500
Well, the sum of the
squared
resistors
equals square root.
Okay.
Okay, so we'll call it 2k. I have a 220 ohm guy and a 330 ohm guy. I'm adding them together to get to 550. I've got 1.9k, which was 1.8 something that I rounded to 1.9. And when I add 41 to it, I've already did that because I rounded it up, so I'm going to keep it 1.9. And then this comes out to 1.97. I'm going to round it up to 2. All right, good enough? All right, maybe. What's the current? We don't have any angle yet, so we're going to have to go for the angle next.
Okay, the angle.
So the arctangent of the inductive guy, which is, we'll go with 1.9k. 1.9k divided by 550. Had to do it twice, but 74 degrees. Way to go.
For degrees?
Yeah, it didn't look like it.
No, it wasn't 1040.
All right. Angle 74 degrees. Total current, voltage divided by impedance. What's the voltage? 5 volts?
Yes.
5 volts divided by 2K angle 74. 2.5 milliamps angle minus 74. Voltage across inductor 1. What's X sub 1? 1.9K. 1.9K angle 90 times the total current 2.5 milliamps angle minus 74. All right.
Sloppy again.
I know. 1900 times 0.0025 equals 4.8 volts angle what? 16 degrees. All right, so you want me to get rid of some of the sloppiness here? Okay, is that good?
Thank you.
Voltage across resistor 1, 220 ohms, 2.5 milliamps, angle minus 74. Times 2.0025. Boom. 1/2 volt angle minus 79 across the second inductor. 40. Oh, the other 74. Angle 90. 2.5 milliamps. Angle minus 74. That's not going to be very much. 1/10 of a volt, angle minus 74. 330 times 2.5 milliamps, angle minus 74.
Is that angle 6? So, yeah, why angle 16?
Oh, this right over here? Yeah, I was just trying to see if anybody would catch it. 16. All right, 330 times 0.0025. Change to a fraction. 33/40ths. Oh, that's pretty stupid. 0.8 volts, angle minus 74 degrees. Okay, good enough. And could I have done it could I have done it all over again and left off all the angles except the phase angle on the bottom? Yeah, I could have. Yeah, so I could have gone and done that. Okay, so now we're proceeding on to section 11 point whatever it is.
Can you go back to the L page? 8.8 volts. Angle 16. Why did you do angle 16?
Okay, I'm in section 11.2, and Raimundo wants me to do what?
What?
What do you want me to do? Go back to here?
No,
Break it.
no, I got it.
You already got it from me.
I got it from us.
Okay.
Corvette.
So now we're on 11.2, and we're talking about apparent power. So when I look at my XY plane, this way I have real power, that way I have imaginary power, and this way I have apparent power. And apparent power is what you're paying for at your meter. Your meter is cranking down apparent power. The angle theta is my power factor,
Freaking symbols are killing me.
is the power factor. And apparent power is going to be equal to the source angle times the total current. Yeah, so whatever the source power supply is times the total current, that's going to be the apparent angle. The total current is going to have some phase associated with it, theta, because there's going to be an inductive component and a real component, so there's going to be some angle associated with it. And yeah, you're right. That was a bad thing to use there. That should be an X. So the inductive power is going to be X of L times the current squared this is going to be at 0 degrees, this is going to be at 90 degrees. This is going to be some power at angle 90 degrees, whatever it is. And real power real is I squared R, and power apparent, because those guys are at right angles to each other, is the square root of the real power squared plus the imaginary power squared, the inductive power. And the power factor is the arc tangent of the imaginary power divided by the real power. No, it's not. The power factor is just the imaginary power divided by the real power. So, and the power factor is also equal to the cosine of theta, the phase angle. All right, time to work some problems again. See if we can find one. Probably number.
My God, now these problems are gonna be
Let's not do them.
dust in the wind.
Looking at number 18. Calculate the component current, voltage, power for the figure below, then calculate the apparent power. Okay, so that's all there is to do. All right, so we got this thing, we got an inductor, we got a resistor, we've got 100 millivolts, 15K kilohertz. We've got 220 millihenry, and we got 5.1 K ohms. All right. So I get a 4.0 for drawing the picture right. Calculate the component current. So I want I sub L. I want I sub R. I want voltage sub L, voltage sub R.
Check your numbers.
I want power X, power R, and power apparent.
Pat.
Okay, so that's all I have to calculate for one lousy point on a test. That's all I have to calculate. Almost as good as whatever the extra credit question is.
Go up, please.
Well, I have to go up in order to solve the stupid problem. I can't do it in my head. All right, so first thing we're going to do is find what x sub L is. 2 pi f L. Okay, so that's the first thing we're going to do. 2 times pi times 15 times 22, 2.1k. 2.1k. Then we're going to find the impedance, square root of 5.1k squared plus 2.1k squared. $5.5k. Okay, now the total current should be the same for both of these guys, right? One would come to that conclusion maybe. So we're going to do that, which is going to be voltage 100 millivolts divided by 5.5k. That's not going to be very much. Way to go. Um, 18 microamps. 18 microamps. 18 microamps. Now it has some associated angle with it, but we can ignore it for right now probably. The voltage across the inductor, X sub L total current. Anybody remember X sub L? 2.2. 2.1K, 18 micro. R, I, total. 5.1K, 18 micro. Okay, 2.1 E3 times 18 E6 minus. We'll call it 38 millivolts. 5.1 times 18. We'll call it 92 millivolts. Now, idiot check. 92 millivolts squared plus 38 millivolts squared, square root had better be 100, right? Because these two have to add up to 100. So I'm going to go 92 squared plus 38 millivolts squared equals square root, and I get pretty close to 100, so that should be good enough. Alright, so the idiot check works. Power x I squared, so that'd be x sub L I squared. This would be R I squared. Okay, so x of L, 2.1K. The current is 18 microamps. That is squared. Resistance 5.1K, 18 microamps equals, and apparent power is going to be the square root of that guy squared plus this guy squared, but I don't know what they are yet, so I can't put it there. Okay, so 2.1 EE3 squared times 18 EE6 minus equals. What? Did I square the wrong thing? Is that what you're complaining about that in the back row? Front row isn't complaining that I squared the wrong thing. Why should you guys care?
That's because they didn't know.
Oh, okay. That explains that. But the front row is supposed to always correct my problems. 2.1 EE3 times 18 EE6 minus squared. 690 nanowatts. 5.1 EE3 times 18 EE6 minus squared equals 1.6 microwatts. Alright, so I've got 0.68 microwatts squared plus 1.6 microwatts squared equals 0.68 EE micro squared plus 1.6 EE6 minus squared equals square root 1.7 microwatt. Is there any truth to that? I wonder. Oh yeah, you have 0.1 volt to start with. You'd expect to have not very many watts, and so I don't have very many watts, so that'd be perfectly okay. That's 18. Number 22 is a parallel guy, and we haven't done anything with parallel guys yet. And parallel guys are a horse of a different color, which means we'll have to do them on Thursday. So bring your toothbrush on Thursday in case we go over. Oh, there's not very many of them. They can't possibly go over.
You know how many